Why don't we get started? So there is a project due on Tuesday involving HTTP. Please make sure you look at it sooner rather than later. If you haven't, you should be looking at it now. So today I'll hopefully get to peer-to-peer. I don't think I'll cover peer-to-peer today, but we'll certainly get through the rest of Chapter 2's material on application layer. The goal is to get through that by end of Tuesday's class meeting. Okay, any question about the homework so far? Yes.
I keep getting HTML search requests, but I can't find any
HTML part?
HTTP. I'm not finding any HTTP GET requests at all.
Okay. You have to make sure if you're not getting any HTTP GET requests, you have to clear your cache. Either clear your cache or do a shift. Hold down the shift key and reload. Because the browser is caching or saving things locally as a convenience to speed things up. In fact, we're going to talk about caching today. And you want to make sure that you force your browser to reach out to the so-called origin server to fetch the content each time. And so it won't give you the GET request if it's pulling it from cache. And so you hold down your shift key and literally there's like that, it's like a circular arrow, which is the reload key. So hold down shift and hit reload to force the GET. Or you could go into your browser preferences and just clear the cache. Okay, any other questions? All right, so why don't we continue on? Where we left off last time, we talked about cookies as a method for implementing some notion of state, even though the state isn't supported at the base level in HTTP protocol. And so state is important for certain things like shopping, e-commerce applications. In fact, shopping carts are implemented using cookies, right? You go shopping, you add items to a shopping cart, and you can revisit that web page, and your cart will still be full with those items. And so on a subsequent HTTP GET request, that cookie information is specified among the header line section of your HTTP GET request. And that web server takes that cookie, that number, piece of information, and looks up an entry in the database and knows that you have added this stuff to your cart. And so this information is rendered, and now your cart information is preserved. Things like recommendations, which was the example that we used when I visited Amazon.com and did a search for something. It doesn't know you in particular, but using a cookie, it can identify your session and therefore present you recommendations based on shopping history. So you could click on, say, Amazon Echoes, I think was the example we gave, or we did in class, and then you could click on, say, Xbox, and maybe you're looking for jackets or book bags or what have you, and then over time, it'll take this information and continue, this cookie information, and continue to add to a database entry associated with your cookie value assigned to you, and update the recommendations. And so the idea here is that it uses the cookie file and cookie information to preserve state information at the so-called endpoints. So the server's database is maintaining information about you, and likewise your local storage at your browser, the other endpoint in the communication, is also maintaining information, namely the cookie entry. Now, in the old days of browsers, I should say old days, in the earlier days of browsers, there was a file called cookie.txt, and you could examine it. And most browser implementations now use some other type of file format, but it's a similar thing from way before. You have a domain name, and associated with that domain name is a cookie number. And when you visit that domain by typing it into your browser field and hit enter, it looks up that domain in your cookie file and then inserts that cookie number as a cookie header line entry. Okay. Any questions about this? All right. So especially if you use internet browsers at public kiosks, even things like the library in the lobby there, you want to make sure that you're careful with clearing the cookie information, right? Even if you don't on your own computer, you want to manage your information state that it saves about you because that opens you up to security risks. Okay. So let's continue on, and let's talk about web caches. A web cache is sometimes called a proxy or web proxy, and as the name would imply, as a proxy, that means it's acting on your behalf. And the user, in many cases, if you want to make use of web proxies, instead of your browser reaching out directly to the internet, it's going to do so indirectly through this proxy. And so instead of contacting, say, Disney.com directly, it's going to contact the web proxy, and the web proxy is going to forward that HTTP GET request or initiate a GET request on your behalf to this content server. Now, in the nomenclature they use in the book, they call it an origin server. And it's called an origin server because it owns or originates the particular content or web objects that you're requesting. And so the web browser sends all of its requests to this proxy, and that proxy is a cache. And as a cache, it has some storage. It doesn't matter what that storage is. It could be volatile, like memory. You turn off the machine and the stuff stored goes away. Or it could be non-volatile, meaning it persists between power cycles of that machine. So something like a disk. So nonetheless, you have a client, and that client makes an HTTP GET request, issues that to the server, the proxy server. And then that proxy server takes this request, and then when it looks for items, it checks locally in its own storage to see if it has a copy of that particular web page or web object. If it does not have a copy, then it goes ahead and it initiates a GET request to the origin server. So then in response, like any good HTTP server, it gets that content and brings it into memory, and it sends it back across the wire to the requester, which in this case is the proxy server. So the proxy server then gets this content from the origin server, and when the proxy server receives this content, it stores it in its local cache, its storage, and then sends back that response to the originator of the request, namely the client. So what happens here? Let's assume that it's a popular resource, like the main page of Disney.com. You're not going to be the only one in a large enough organization that's going to visit that content or visit that site. So what happens when the second person comes along, types in www.disney.com, for example, and decides to load that web page? So his or her request likewise gets sent to the proxy server. Now this time, for the second request that's come along for that same content, Disney.com, it consults the cache server or proxy server, and this proxy server, for each request for some object, it looks locally in its disk first. And so this time, because it's already been stored in the cache for this proxy server, it finds that this content does exist locally. So rather than initiating a new request to the origin server to load that content over the internet, it takes it from its disk. So that's a total savings, so you don't pay the cost of that transfer time across the wire. It takes it from its disk, loads it into memory, and then immediately satisfies that request and sends the content back to the client. Does that make sense? And so this is predicated on the idea that a lot of popular resources, more than one person is going to want to fetch that resource, that web content, those web objects. And if multiple people are going to fetch that, why spend the cost each time per request to reach out across the internet to the origin server to fetch that content? If you cache it locally or store it locally on the same network, then you save all of that trouble on the second and the third and the fourth and every subsequent request for that same content, right? Okay, any questions about this? Does that make sense? Okay. So let's take a look. The cache is technically a peer, right? It acts like a server when it's returning back content to a requesting client. It acts like a client when it's requesting content from the origin server. And so typically, you might ask, well, where's a cache installed? You can install a cache anywhere. Typically, a cache is installed in any organization. We have sufficiently large enough group of people that this will make a big savings, this local loading, rather than reaching across the internet to the origin server. And so, like a university, you might install a cache, an internet service provider, residential ISP might install a cache, or a business. There's nothing special about caches. You can install one yourself. There's absolutely nothing special about them. In fact, one of the largest usages of bandwidth on DSU's campus is Netflix. And guess what? There is such a thing as a Netflix cache, right? You have to pay for it. But if you think about it, the cost of a Netflix cache, I believe it's like $5,000 or $10,000 a year. That's nothing compared to the monthly cost of having large bandwidth off campus to the broader internet, the organizational trunk line. You can afford less bandwidth if you're caching locally. So, some blockbuster movie comes out, maybe 100 people are gonna watch it. Without a cache locally, now each one of those 100 browsers is fetching that streaming content directly from Netflix's data center. Whereas if you had a Netflix cache on campus, well, after the first person watches that movie, those other 99 browsers are loading locally on your local area network instead of pulling content across the trunk line between DSU and the service provider. So we'll have an example that shows you in real number terms what the savings are for installing a cache. And if you think about a cache, it's just a simple machine, right? You pay a one-time cost for that machine, you set it up, rather than that recurring cost of the monthly subscription for an increased trunk line for bandwidth. So why do you do caching? Certainly, it reduces the response time. And the reason why you reduce the response time is that you're now trafficking data on your same network. And it's a lot easier to send things back and forth locally than it is to request things over the internet, right? Because as we said before, congestion is a real thing. And especially if you lose data at the end or closer to the destination, you're gonna pay a large cost of having to establish that pathway for your flow, right? So you reduce the response time and you also reduce the aggregate traffic on the outgoing link. And so if you think of DSU's network as this big cloud with a bunch of machines that are interconnected, there's a router that is that last point over which all DSU's data goes, making its way to some service provider. Now certainly, I hope, and I don't know the network architecture of the campus, I would hope that they have more than one link or redundant links off to a service provider. But nonetheless, you have a small number of links to service providers over which travels all the aggregate traffic for the campus. And so when you have a cache, because you're reducing that burden of reaching out to the origin servers, you're now just getting that stuff locally, that request and that content never leaves the network. And the end result is a reduction of traffic in the institution's access link to the service provider. If you have a network and you have a lot of caches, that essentially makes you a content provider if you think about it. So let's say if we had a Netflix cache on campus, and we had a Disney cache on campus, and we had a Hulu cache on campus, all of a sudden, DSU looks like a content provider because all of that content from each of those content providers is now being served locally from the cache instead of all the way across the internet, across the institutional access link to the origin servers. So there's a lot of benefit for web caching, and it's a very relatively inexpensive thing to implement. Any questions about this? So let's take a look at a typical scenario. And in this diagram, we have the internet, okay? So you have the usual things. You have an access network for the data center, for the origin servers, for a content provider. You have maybe a regional and a global ISP with some switching fabric. And then you have some gateway router to get you from the service provider's network to DSU's network, for example, right? And so this router, gateway router, is responsible for pushing as well as receiving all of DSU's aggregate traffic as well as content from origin servers back and forth across the institutional access link to get to the service provider's infrastructure. And ultimately, that traffic makes its way all across the internet. And so you have some configuration of machines at DSU. And you can, it's very typical these days to have 1 gigabit network speeds on the local area network. So 1 gigabit is pretty fast. In fact, right now in Dover, you can get gigabit Ethernet from the Verizon Fios product to an individual household. But nonetheless, gigabit is this pretty large pipe, if you will. It's a large amount of data, gigabit per second. So in this example, and this is in the book, The average object size is 100 kilobits, right? Kilo is 10 to the 3. So 100 kilobits is the average object size. And for the sake of argument for this example, each browser is requesting content from the origin servers at a rate of 15 requests per second. So if you want to know the aggregate amount of traffic that's flowing from the origin servers for these objects back to the institutional network, you'd multiply this 100 kilobits times this 15 requests per second. That's 1.5 megabit per second. Okay. So that means on average, data is flowing from the origin server back across the institutional access link to the institutional network at a rate of 1.5 megabit per second. But at the same time, maybe DSU has subscribed to an internet service provider and they've purchased a link that's 1.54 megabit per second. Now, obviously, for an institution the size of DSU, for the type of rich media in which lots of people are trafficking, this is going to be woefully inadequate. And if you take the amount of data flowing, 1.5 megabit per second, and you divide that by the total capacity of institutional access link, 1.54 megabit per second, you're utilizing, with this example, 99% of the available link bandwidth. And as we said before, when we talked about this idea of traffic intensity, that the closer you are to the upper capacity at which data can be pushed out and pushed in, you start to fill up your router buffers and you start to get queue delay to the point where eventually your buffers fill up and you drop a packet. So the more you saturate the bandwidth of a link and a router, the more likely your flows are going to take longer to get to their destination endpoint. So we have link utilization in this example of 99%. So that means you're going to have on the order of minutes is the time it's going to take for those messages to make it across that link. Now, of course, it's just drawn as a single link, but that's not how it happens in practice. But still, the same ideas apply. Any questions about this? So let's take a look and make an accounting for all the sources of delay. So certainly, if you're pushing data over the institutional network, you're going to incur a delay. Now, the institutional network operates at a gigabit per second lag. You can get category 6 cable and easily get gigabit switches and have gigabit speeds on your local area network. So that's going to take on the order of microseconds. It's not very long. It's really, really fast to traffic and data over a gigabit link because we're not there yet in pushing gigabits worth of data from the set of devices that people have that are generating and consuming content. So in order to get information from your origin server back to your network, well, you have to go across the internet from the origin server to this institutional link, this gateway off the service provider. That's called internet delay. It's the amount of time it takes for content to get from the origin server back to the gateway before it makes its way onto the institutional access link. So then you have the access delay, right? And that's the amount of time it takes to get from the ISP to the gateway of the institutional network, right? So to push traffic from the origin server to any machine on the institutional network, you have to go across the internet, across the access link, and then across the local area network. So we have internet delay, which is on the order of seconds, like 2 seconds or so for the internet delay to get to the gateway for the ISP. And then you have the access link delay, that's to get across the access link onto the network of the organization like DSU. And then you have the local area network or LAN delay to get from the gateway on the institution side of the network to an arbitrary machine that is the consumer of the content. So when we look at that accounting, you consider the 3 components: internet delay, the access delay, and the LAN delay. When you talk about the order of how long it takes to get your content from the origin server to some machine endpoint on the institutional network. Does that make sense? Any questions about this? So let's look at this accounting. So the internet delay is about 2 seconds, okay, so they include that in your total delay. And then the access link delay. As we just said, using these numbers for 1.54 megabit per second access link, That's 99% saturated, meaning 99% of the available bandwidth is being used up. And because that is so close to being completely filled, utilizing all the bandwidth, we're going to have a large delay because those router queues are going to start to fill up, right? So 99% is very close to fully saturated, and you're going to see minutes, on the order of minutes, delay to send data across the access link to the institution. So then, of course, once you get to the gateway router on the institutional network, you're going to see microseconds because you're barely using any of the bandwidth of that local area network. At 1 gigabit per second, using these numbers, you're using about 15% of the available bandwidth, which is next to nothing. It's not really that much, right? And so we have here, if you add these three components up, it's going to have a delay of minutes, right? Because the number of minutes it takes to traffic that content across the institutional link is going to dominate these 2 seconds and dominate that microsecond. Okay. Any questions about this? And so that speaks to this idea of the so-called bottleneck link. What matters in your end-to-end flow, or what dominates the performance in an end-to-end flow, is the slowest link along the route. Okay. And here we see the access link is going to dominate the time it takes for some object to get from the origin server back to some browser on the institutional network. Now you might ask yourself, gosh, well that's horrible because you don't want a frame of a movie in Netflix to take minutes to get to your browser, right? You want to see that thing in the order of milliseconds, because otherwise your movie, you're going to see like 1 frame and then a few minutes later another frame. And that's no good for a movie, right? Okay, so what can we do here? Let me ask you, what would you do here? What could you do?
Cache it locally.
You could, that's the answer. Yes, you can cache it locally, and we'll get to that. Okay, well, thank you for reading the slides. So one of the ideas, if you weren't sophisticated like all of you, you could say, you know what? Since this is the bottleneck link, I'm going to increase my link capacity. So I'm going to go to Verizon and say, hey, this access link that I'm paying maybe $1,000 a month for, I want to increase it tenfold. So it's going to cost me maybe another $8,000, $9,000 or $10,000 a month to have a tenfold increase in bandwidth. Wonderful. Now, of course, the ISP isn't going to say, use a cache, you'll save money. No, they'll gladly take your money. You're asking for something, they'll sell you something. They're in business to make money. So you decide you're going to increase the width, bless you, of this link, right? And you do that tenfold, all right? So now, or not tenfold, 100-fold. If you increase it 100-fold from 1.5 to 154, it's going to cost you a lot of money, right? As you can imagine with any sort of home internet package, if you go from 25 megabit to tenfold, that's 250, and then another tenfold, that's 2.5. So if you went from 25 megabit to 2.5 gigabit, that's going to cost you a lot more money. But nonetheless, they'll sell it to you if you increase the link capacity. So in this case, let's say you increase the capacity of the access link. That's not correct. That should be 99%. That should be 15.4, not 154. That's why I got thrown off. All right. So you increase the link capacity. If you increase the link capacity tenfold, it's going to cost you more money. But guess what? Now your utilization goes down from 99% to 9.9%. If you increase it 100-fold, it's going to go from 99% to 0.99% utilization. Now, let's just take the assumption of increasing it tenfold. If we increase the speed tenfold, it wouldn't be 154 megabits per second for the bandwidth of the institutional access link. It would be 15.4 megabits per second. So just imagine this said 15.4 for the sake of this example. So going from 1.54 megabit per second for the institutional access link's bandwidth to 15.4 megabit per second, now your link utilization, given the same request rate and size of the objects, you're going to now be down to 9.9% utilization for this access link. So that's relatively small, and because of that, it's going to go from minutes delay to traffic data across that access link to milliseconds, right? And because it's pushing out data at a rate that's so much faster than the data comes in, that means that your delays are going to be small because your router buffers are not going to fill up very much. Does that make sense? Any questions about this? So given that, okay, our numbers change. Well, our local area network delay is going to be on the order of microseconds. Our internet delay, that hasn't changed. You really don't have control over that. That's going to be about 2 seconds, given these numbers. And then, of course, now we've reduced the bottleneck link. Instead of minutes, it's now milliseconds because our utilization is so much smaller now. And so what dominates here is the 2 seconds. And so that means our delay is going to be around 2 seconds because the 2 seconds is much greater than any amount of milliseconds and certainly greater than any amount of microseconds. Okay? Now that's really kind of what you want, right? You want the thing you can't control to be the thing that dominates your access. The other stuff you can control. And in this particular case, the choice was to increase the bandwidth of that institutional link. Now you might say, wonderful, great, I solved the problem. But absolutely, it does solve the problem. But one of the drawbacks is this idea of a recurring cost. In order to do that, it's like changing your Xfinity or your FiOS package. You have to pay that monthly, right? Month after month after month after month after month. Now, certainly if you're paying this monthly, if it's a significant cost increase, of course, you're going to be shelling out that money, and that translates at DSU to increase student fees. Welcome to your student fees. Nonetheless, that's a recurring cost. And in any sort of engineering situation, you want to try to balance things out. What is important to incur as a recurring cost versus a fixed time, one-time cost? So let's take advantage of caching, and you'll see that you can get an improvement far better than this recurring cost of increasing the link bandwidth. You can get an improvement with a financial benefit of a one-time cost. Okay? All right. So it's not cheap to increase the access link, and in fact, when you increase your speed, it's not a linear increase in cost, right? So if you go from 25 megabit per second to 50 megabit per second, they don't charge you twice, right? That curve is not linear. And so if you went 10 times, it's going to cost you probably a lot more than 10 times to have that type of increase. Okay, but they'll gladly sell it to you and take your money. All right, so let's look at the scenario where we have a local web cache. And for this, we go back to the original scenario where we had an access link whose bandwidth was 1.54 megabit per second. So that hasn't changed. We're paying the cheaper price, as it were, for this slower access link. And so the internet delay has not changed. The LAN delay has not changed, 1 gigabit per second, but we've paid maybe $1,000, $2,000 for a machine, and we're going to install it as a server, the operating system, and we're going to run this cache. And so now all of the browsers on your institutional network, instead of going directly to the public internet, they're going to connect to this web cache. So let's see what happens. So it's very cheap. It's just the cost of a machine, certainly the cost of electricity. Every once in a while you have to maintain it, make sure it's running the RAM and all that other good stuff. Now, how do we compute this delay? Now, there's a notion called a cache hit and a cache miss. A cache hit corresponds to a request for some object that exists in the storage of the cache of the proxy. A cache miss refers to the scenario where your browser is requesting an object and that object does not exist in the cache. If it does not exist in the cache, i.e. a cache miss, that means the proxy server has to request that from the origin server and load it across the internet, incur that delay, store it in its local memory before returning a copy back to the requesting client. So let's assume, and this is typical, often for very popular items, it's even higher, but let's just assume, and these numbers are in the book, that 40% of the time a request is satisfied by the cache, meaning that you have a cache hit, right? And let's assume also the converse, if 40% are in the cache, that means 60% are not in the cache, it's a cache miss. So that means 60% of the time, the proxy server has to go and fetch that content from the origin server. So what does that mean? That means that 60% of the time, you're going to incur the full cost instead of going to the cache server, you're going to go across the internet. So 60% of the time, bless you, you're going to pay the full cost of trafficking in data across this institutional access link to the origin servers and so forth. So that means that 60% of our requests are going to use the access link. So 60% of the time you're going to use the access link. That means we take our full data rate, which was 1.5 megabit. That was 100 kilobit times 15 requests per second. That's the full stream of data. That means we multiply 0.6 times that 1.5 megabit. That's 0.9 megabit per second. Now, if we take that 0.9 megabit per second, how much of the link utilization are we talking about? Well, that results in 58% link utilization. That's not too bad. You'd like it a lot lower rather than higher, but it's nowhere near 99%. So most likely, if you're dealing with 58% link utilization for the institutional access link, what that means is that your router buffers, maybe they might fill up here and there, but they're not going to be anywhere near close to being almost full. So that means that you're going to incur relatively small delay as it pertains to trafficking in data across the institutional access link. So we have this utilization of 58% as a consequence of the reduced load across the access link, because 40% of the time that those requests are satisfied by the cache and not having to reach out across the internet to the origin servers. Does that make sense? Any questions about this? Okay, so let's take a look at our delay calculation. So you say 0.6 for 60% of the time. You're going to incur a delay for going all the way to the origin servers for your content. And then 0.4, representing the 40% of the time, you're going to incur a delay associated with satisfying your request of the cache. So let's take a look at cache access for your content. So with cache access, well, it's very fast. Even with a large amount of data, it's going to be very fast. It's certainly going to be on the order of milliseconds. I dare to say sub-millisecond, right? And so we say milliseconds times 0.4 corresponds to the delay you incur when you load things 40% of the time from the cache. So the remaining 60% of the time, well, we just said the access link is only loaded 58%. So you're going to incur a very small delay on the order of seconds, and that's going to be dominated by the internet delay, right? When your link is not fully saturated and it's not close to being fully saturated, you might even get milliseconds of delay in terms of the performance, the traffic data on and off of that link. Okay. So we multiply our 0.6 for 60% of the time, and that 2 seconds, which is dominated by the internet delay portion for reaching out to the origin servers, and we get roughly 1.2 seconds. And we notice here, just for paying that one-time cost of installing a cache, given the slower access link, now we have a delay that's even smaller than that recurring cost of 10 times the bandwidth for the access link. So you can really get a so-called good bang for the buck, really efficient use of money, and get significant performance improvements by just using a cache server. And all it takes is really the cost of buying the machine and the cost of running that machine, which is significantly cheaper than paying the monthly subscription for the increased bandwidth. So if you're in a data center or some other scenario where you're dealing with objects that are frequently requested, you want to do the analysis to ask yourself, is it cheaper to install a cache versus just making the simplified assumption of just increasing the bandwidth? Does that make sense? Any questions about this? All right. So that's the beauty of caching. And in fact, a company named Akamai, I remember when I was in graduate school, Akamai really started, they started to get really big. Akamai, their business is caching, right? And so sometimes, well, I won't say it now, I'll wait until Tuesday, never mind. Maybe next week, Thursday. I'll save that for another time, let you find out for yourself. But Akamai is a company that specializes in web caching. And I'll just stop there. All right. So how does caching work? Well, if you're going to cache something, you want to know that you have the most current version of some object. And so you stamp all web objects, whether they're files or videos or what have you, based on the timestamp. And so in the header line section of an HTTP GET message, there's one type of header line entry called if modified since. And so you have your browser, and your browser has gone to Disney.com, and a JPEG image that's displayed on Disney.com's website is loaded on your local machine. So now you do a conditional get, you type in www.disney.com, and then all of a sudden, Disney has updated their web page with a different JPEG, right? So what your browser does, it says, gosh, well, I know that there's an image that's in this browser, and I need to know whether or not that image has changed, because I don't want to have to reload it every time, because images suck up a lot more bandwidth than just plain flat text. Same thing could be for HTML files, but they don't usually do that with HTML files. This is typically for objects, because objects take up a lot more bandwidth when you're loading them back across the wire. So what happens? There needs to be a method to say, don't send the object if the cache has an up-to-date version. So if it's not up-to-date, meaning that if there's a new version on the origin server, right, then go ahead and retrieve that object. If there's not a new version, well, don't retrieve it. And so how that's accomplished is with this if modified since header line entry. And so it says if modified since, and then that's the name. The value is the current date associated with that particular object, which is in the get request. So the server response can contain one of two things. It can either contain a new copy of that object if that object has changed, its date is newer, or if it's not newer, it'll return this 304 not modified response. And so some of you have probably seen the not modified response if you don't explicitly clear your cache on your browser. So here we have a client and we have a server, and the client sends an HTTP GET request. It also includes a header line entry if modified since, and it has the date, which is the current timestamp associated with the object of interest in this HTTP GET request. So then the server gets it, and the server takes this if modified since date, and it compares that timestamp against the timestamp of the file that's in this local drive. If it's the same date, it sends back a not modified message, right? And you use your local copy. Now you notice here this not modified, it's just HTTP text response. That can fit within a packet. It's very small, doesn't take up a lot of bandwidth, and that object does not exist in that response message, message 304, okay? Or response 304. The second thing that can happen, the second scenario, you send your HTTP GET request for a particular object. You include the if modified since header line entry with the timestamp of that object of interest. So that message gets to the server. The server checks the date of the object against the if modified since timestamp, and it says, oh, wait a minute, the date of this object on my local storage is newer or more recent than this if modified since timestamp. So that means I need to send a response containing the new version of the object. So it takes that object, puts it in memory, it gives you an OK message, and there's payload data containing the bits of the object. Any questions about this? And so this interaction is the interaction between the requesting machine, the caching machine, the cache proxy, and the origin server. Because it doesn't always load from the origin server, but it does check to make sure if it needs a new copy. Any questions about this? Does that make sense? So this is actually something you can see yourself, and I believe on the assignment in Wireshark, you'll actually look at this as one of the experiments. Okay. Any questions about this? Make sense? And the idea is that it's much cheaper to send back an HTTP response than it is to send back that object as payload. And that results in a savings in bandwidth. All right, so let's take a look at some of our web applications or internet applications. I would dare to say the killer app for the internet in the beginning was email. Yeah, the World Wide Web was nice and had the graphical internet, but the first real killer app that caused people to, casual users, not just researchers and stuff like that, who use the internet was email. The idea that you could send a message and right away they would get that electronic message. It was wonderful. And so electronic mail is based on this protocol, SMTP, Simple Mail Transfer Protocol. And this SMTP is responsible for transferring the text of your email from one mail server to another. The idea of having a username with the @ symbol identifies an account, and that is associated with an identity of an individual whose account lives on a particular mail server. Now, the domain name identifies the machine on which this SMTP server sits. So SMTP servers can both send email as well as receive email, and therefore you could call them SMTP peers. So we have a bunch of components in electronic mail. We have the so-called user agent, and that corresponds to the email program that you use. It doesn't matter what platform you're on. It could be an actual piece of software. It could be a web browser using webmail. And in the early days, you'd actually have to buy software that was your email client, and it would cost you like $20, right? It's kind of weird for today, but you still have to go on the App Store for mobile devices, pay for things like fancy mail clients and stuff like that. You also, in addition to the user agent, you have your mail server. And that mail server consists of two components. One is the so-called outgoing message queue. Now, in the outgoing message queue, that's where any message that's sent lands. So you compose an email and you hit send. It's not sent immediately. It's stored in the mail server because it tries through some configurable parameter for some amount of time. Sometimes it's usually 2 or 3 days. It tries as much as it can to make sure that your mail gets delivered, right? Now, sometimes you just send the mail and, a day later it'll say, sorry, I couldn't send the mail, right? You have to try it again. That message has to be stored somewhere, and where it's stored is in the outgoing message queue. Now, the mail server also has what's called a mailbox. And a mailbox you can think of as a database storage pool, and there's a single unit of storage associated with each unique account on that mail server, right? And so if you're a user named Bob, then there's a mailbox on that mail server storage for Bob's emails. If your username is Mary, then there's a mailbox on that email server storage specifically for Mary. So now when an incoming mail message arrives that has a username identifying the account, it makes it to the machine, and so the mail server gets it, it sees that username, and it looks up which mailbox is associated with that account name, and then it deposits that email in that mailbox. Okay. Any questions about this? Does that make sense? All right. So we have the user agent, the mail server, and then of course we have the protocol, SMTP, Simple Mail Transfer Protocol, which is the set of behaviors that mail servers engage in order to send and receive email, exchange data with one another. And so mail servers using SMTP, it's built on top of TCP, so it's a reliable data transport that's needed to send email. So I already said that. All right, let me skip this one. So the port number used in TCP, the reliable transport, is port number 25. And now SMTP is sort of going away. And the reason why it's going away is because it's not secure, right? If you have somebody using SMTP with something like Wireshark, you can intercept these mail messages and actually read what people are writing to one another. Most modern email use encryption in order to send back and forth. But SMTP is still there, and you can still install it and try to use it if you choose to. And so if you decide to use an email system, right, I don't imagine most commercial email systems still use plain SMTP, but you should make sure that it is encrypted, because you don't want someone using something like Wireshark to intercept all your emails and know what it is you're talking about. So with SMTP, servers direct transfer messages to one another. So you have a message that's going to a particular domain name. You use SMTP, you contact that server via TCP, and then you send all of that data over persistent persistent connection. Okay. So there are 3 phases of transfer. There's the handshaking. So you have to communicate in order to establish resources to successfully engage in this single mail transfer protocol. And then there's the transfer messages, the actual sending of those emails, and then there's the closing of the connection. And so emails are in ASCII text, but to make this more safe, modern email systems encrypt this ASCII text so that people can't sniff your data as it's going across the wire. Okay, so this is a scenario. Let's say you have two users, Alice on the left and Bob on the right, and Alice opens up her user agent, her email program, and decides to send an email to Bob. And so she sends Bob the account name at someschool.edu, and she hits send. Alice's user agent sends a message to her mail server, and the mail server places that message in the outgoing message queue. So certainly Alice isn't the only person associated with that mail server, whose account is associated with that mail server. Other people are as well. So you're going to have a lot of outgoing messages being deposited in the outgoing message queue. So the mail server picks messages from the head of the queue, and then it examines the account name, and it also examines the domain name. It looks up the IP address for the domain name, initiates a connection via TCP, reliable data transport, and then it sends that email message across the wire directly to the SMTP server, waiting on the correct port number to receive that. And so the receiving machine, Bob's email server at someschool.edu, so that's a machine at someschool.edu, whatever that IP address would be, it gets those mail messages. It takes that mail message, it looks at the recipient account, Bob, and it says, aha, Bob's inbox is over here. Let me open up the inbox, and I'm going to store this message or place it in that unit of storage associated with user account name Bob. Okay. So then Bob, at some point, opens up his user agent, his email program, and you notice here, Alice could send the mail and then detach from the network the moment that message is in the outgoing mail server queue. Likewise, Bob doesn't have to physically be present in order to receive mail. Bob fires up his user agent, and through his user agent, it contacts the mail server, and when Bob proves that he is Bob with the username and password, the correct password, then it connects to the mail server, and the mail server says, okay, you've proven to me that you are Bob, let me go ahead and open up that unit of storage for Bob's email, Bob's inbox, and mailbox, and let me now give you all of the messages that have been placed there. Any questions about this? And so all of that happens in just a second, which is kind of the beautiful thing about this. All right, so I'm not going to talk about SMTP because this is largely defunct, and it's hard to do these sort of demos in class since most modern email does not encrypt. But years ago, you used to be able to connect to an email server directly and compose an email. And the particularly damning part was you used to be able to send an email with a from address that was fake, right? And so I remember when I was an undergrad, we thought it was funny. We'd send each other emails from the president or from celebrities or, stuff like that. But these days, things are much more different. And there's a lot more authentication, endpoint authentication, validation of email addresses, encryption that happens. And it's just too hard these days to do that without setting up a dummy email server. Okay? All right, so I'm not going to cover that stuff. But SMTP uses persistent connections. It opens up a single connection, and if you think about it, why would it do that? Because it's a lot less efficient to open up a unique connection for every single message, right? Because you're going to pay that cost of the round trip time to open up that connection and then send that data. So it keeps the connection open, and it just pushes subsequent messages down that single connection directly to the other SMTP server. Okay, and so when you look at how data flows, for HTTP, you request something, and then that object comes back on the round trip, on the return path. And that's called data pull, right? With SMTP, that data gets pushed out in a forward direction, you can imagine it. And when you design any sort of web or any sort of network application, it's really important to understand what is the best semantic or behavior in terms of how data flows across the network. There are drawbacks and there are advantages for each one. With pull methods, you only get pay the cost of that data traveling across the wire when you need something. But the problem with pull is that if you need a lot of data, one after the other, after the other, after the other, you have to now make another call, make another call, make another call to request that data. With push, one of the things you can do with push is that if you have a lot of pieces of data to send, you open up a connection and you just flood the wire with all of that data that you want to get to the other communicating endpoint. Typically with data push, you have this notion of a timer, right? You say, okay, I want to start sending stuff over this connection for a specific amount of time. So there are trade-offs, and certain types of applications fit well for pull versus push. So for example, if you're implementing a video streaming type of application, you would never want to do data pull for a video application. Because you don't want to say, request the first frame, request the second frame, request the third frame. Because if you do that, imagine at 30 frames per second, and you have a 1 hour movie, that's now 30 times 3,600, and that's the number of frames you're going to have to request. 60 seconds in a minute, and then 60 minutes in an hour. So that's 30 times 60 times 60 is the number of requests you're going to get. And what that means is that your request messages are going to dominate the bandwidth when you want to save that bandwidth for the actual data. So for something like video streaming, you would never have data pull, you would have data push. You would make one request, give me this file, you identify the file, and all of a sudden it's pushing this file towards you, and you don't have to explicitly request every single frame of video. And so when you design your network applications, you have to think of the so-called data flow, right? And when you have data flow between two communicating endpoints, you have two choices about how you can deliver that flow. One is using pull, and one is using push. And that's a really important consideration when you write your network applications. Any questions about this? Make sense? All right. So I'm not going to talk about the message format. Let's talk about that last portion where we talked about Bob firing up his user agent and collecting that email. Now, there's something called a mail access protocol. And the mail access protocol is another protocol that your email program engages with your SMTP server in order for you to be able to connect to it to retrieve your messages and or send your messages. And so SMTP is purely a conversation between mail servers. It's how mail servers send mail to one another, and it's data push. Now, what this mail access protocol is a method used by the user agent to allow the user to access contents of the mailbox, right? And so there are some popular ones, and you can have all sorts of other things, but Post Office Protocol, or POP, is a very popular mail access program. Sometimes if you set up your phone to access your DSU email, they'll ask you, do you want to use POP or POP version 3, or do you want to use IMAP? IMAP stands for Internet Mail Access Protocol. Now, these protocols are in their details specified by the RFCs listed. You can Google search them, they're open standards. Now, what POP does, POP says, I'm going to access messages, and the default behavior in many implementations is to authorize your access, prompt you for your name and password, and then download these messages off the email server. Now, in the development of POP, going from version 1 to version 2 and now version 3, it was widely recognized that maybe that's a bad idea, especially as computers started to proliferate, right? And the reason why it's a bad idea is that if you download your email off your inbox on the server, it's not there if you need to look at it from another machine. So what that would mean is that you're at your desktop at home, you read your email, and then you go to your machine at work, all of a sudden, the server doesn't have it, right? And in that case, it would download the email to your device, and it would now travel with your device. And so later versions of POP added the ability to just download a copy, but leave the original emails on the server. So that way, any device you use will download a copy, and you can collect your email from anywhere. But you can still absolutely set things so that you download from the server, and that means they're gone if you try to access it from another device. Now, Internet Mail Access Protocol, it was designed for the messages to remain on the server, but it also associated meta information with your data, this idea of folders, right? Now, IMAP came along when email started to really catch, and people were using email for all sorts of things, especially business, everyday things. Now, of course, you get a lot of emails. And when you get a lot of messages, you want to organize them. And this idea of designating folders now allows you to tag emails associated with a particular pool of storage, namely your folder. So now you can have messages that are work messages, messages that are private messages, and now you can set these filters that will automatically look at who it's from or scan for keywords and deposit this message in a folder. And the nice thing is because IMAP assumes that all this meta information as well as the emails remain on the server, you just log into the server from a different user agent and your folder structure has been preserved, right? It's why you can go to your Yahoo Mail or go to your Google Mail from different places using different browsers, and the folders you've set up still exist there. It's why you can go to Outlook Express, and why your folder structure is there regardless of where you access it from. If you access it from Outlook or you access it from webmail, it's the same folder structure. So that's Internet Mail Access Protocol, and it allows you to manipulate those stored messages, change these associations with folders, and most modern IMAP clients, user agents, allow you to set these automatic triggers so that you can organize your emails. Now remember, before we had Slack and before we had Blackboard, a couple years, well, like 8, 9 years ago, I would use email for my classes, and I would insist that students use the class name CSCI 330 if they're emailing me about that class, because I'd set a filter and I had a separate folder for each class, and when I got a folder in the subject line CSCI 330, it would automatically drop it in that folder, so we'd have to go hunting through hundreds of emails a day in order to look for questions that people had. But now we're much more sophisticated. We have things like Slack, and it does notifications for you. But nonetheless, IMAP was a huge development when it came along. Then, of course, there's webmail. And the beautiful part about webmail when it came along is that browsers started to become much more ubiquitous. And in the early days, when you had just regular user agents, whether it was a POP protocol, POP3, or IMAP, you had to install your email software, your email user agent. And so if you wanted to update the behavior of how this email access worked, you now had to convince people to install new software. And that was a royal pain. And imagine if you're a company, and let's say you have a corporate workforce of like thousands of people, now you have to get thousands of people to bring their device in and actually update software. Now, this got a lot easier with electronic updates, wonderful, but in the earlier days, you actually had them bring into a service desk, and someone had to take the time, like at Best Buy, to actually physically install something on their computer to upgrade your software. So what webmail did, it said, okay, well, if I want to change the look and feel or behavior of the email, for example, at one point in the past, Gmail updated their interface. All you do is just reconnect to gmail.com and you get the new interface. And there's a little button that says, you want to use a new interface? You say yes. It just directs you to a new version of the web page, and all of a sudden, it's a new interface. Nobody had to install anything on the machine. And so webmail came when the World Wide Web started to become more ubiquitous, and what it allows you to do is change your interface, effectively change your mail software without having people come in and have to install software or do physical upgrades. Okay? All right, any questions about this? Does that make sense? So that's why web-based applications are so popular, because you don't have to do anything as a vendor to really change. You just go to the website, and all of a sudden, the look and feel is different. Okay, any questions about this? So let me check the time. It's 1:01. Okay, we have about 14 minutes. So I'm not going to talk about all of these. I think I already mentioned them in some way before. So POP downloads, they changed it so that it keeps stuff on the server. IMAP associates folders, and that stuff travels with the server. So if you try to connect to it from different devices and different locations, different computers, it's always the same. Okay, so let's take a look at DNS, domain name server. Now, we've talked about things like sumschool.edu and disney.com, and you're all very familiar with desu.edu. These so-called domain names are text descriptions, and their only purpose is to make things comfortable for us. right? People are really bad at remembering numbers, but really good at remembering names. And moreover, if you have a name of a company like International Business Machines, IBM, gosh, if you're trying to remember the website, aha, IBM.com. If you're trying to remember the name of Google's website, what's the company's name, Google? Google.com. So using names is purely for the benefit of people, but at the end of the day, the computer only really cares about the numerical address. And so domain name system is a distributed database, and its whole purpose is to be a translator, if you will, that will map between these text names that are useful for people and these numerical names, which is what the computer really cares about, specifically the network layer. And so internet hosts and routers all have a unique IP address. It's 32 bits. That's IP version 4, but certainly IP version 6 is becoming more and more pervasive. And so a name like yahoo.com is used by people, but a number like, I don't know what their address is, I'll just make one up, 164.27.93.14, all right, is what your computer really cares about. And so the question that DNS answers is, how do you map between names and addresses and vice versa? And so domain name system, or DNS, is an application. And as an application, you might think, gosh, well, why is an application trafficking in information that is meaningful to the network layer? It's sort of a violation of layering technically, but it allows you to keep this complexity at the endpoints and outside of the network core. And so that was a really important decision that they made when doing this name mapping system. And so it's a distributed database, and it occurs as a hierarchy. And so it's an interconnected set of servers that participate collectively in the mapping of names to numbers. And so it's very key to the network's function. And I'll explain a little bit how you might run name server resolution. And so DNS services, what does it do? It provides a bunch of different services. One is certainly mapping host names to IP addresses. So it does this translation. It also allows you to alias things. And I'll give you an example of what aliasing is. If you have more than one server, and those servers collectively are giving you the content of, say, IBM.com or gmail.com, you want people to access it as gmail.com, not Eastern server in the northern part of Maine, server number 7, google.com, right? It allows you to do what's called canonical naming, so that you can alias multiple copies of a domain name for the same entity. It allows you to alias your mail server, because maybe you want to send email to desu.edu and not mail.desu.edu, or not East Coast Dover North Server 2 at desu.edu, right? So you can alias for mail server. You can also do load distribution, and I'll show you an example of that, where you have more than one instance of a server that looks like it's a single domain, because you want to send that request to one of some number of instances in order to distribute the load. So DNS is not centralized, and the reason for that, because it's so critical to accessing the internet, you don't want a single point of failure, and you also want to balance out the volume of traffic. You don't want to send 1 million people's DNS requests to one server instance because it's going to break, right? You want to spread that request load out to a bunch of different server instances. It's decentralized, and it also makes it easier to maintain. So let me pop out of here briefly, and I'll show you an example of using DNS queries, or issuing DNS queries from the command line. So I'm going to pull up my terminal. Oh, that was from my other class. I'm going to pull up my terminal, and for the Mac, it's ns lookup. It's usually for most Unixes. Clear. ns lookup. Let's say desu.edu, right? And so here it says the server is 192.168.2.42. That's the IP address of desu.edu. So when you enter www.desu.edu, addresses associated with that particular property. Let me just try one last thing. See that? Yeah. So here, if I say mail.google.com and its lookup, it'll tell you what the canonical name is, right? And then it'll tell you what the alias name is. And then it'll tell you the address for that canonical name, right? So, things change even from, 6 months ago to now. So I'll show you a better example for that next time. So let me check the time. We have about 3-4 minutes. Okay, so let me go back to DNS, and I'll probably end on the next slide. To have a single point of failure, it does not scale. And if you think of all the people that need to resolve names, it's everyone who tries to access the internet. And so this service must be distributed. And so DNS is arranged as a bunch of servers, and more correctly, a bunch of data centers, not individual servers. And the namespace that you use is divided up into a hierarchy. At the top of the namespace, you have what are called the root DNS servers, and these data centers are dotted throughout the world. And if you entered the null URL, that would be served by the root DNS servers. Below the root DNS servers, you have the DNS servers that manage the so-called top-level domains. These are things like .com, and so you notice the name might be IBM.com or DESU.edu or some name .net. Now that suffix after the .com, .net, .org, and there are different countries that have their own domain suffixes. And so you have different so-called top-level domain servers whose entire job is to handle mapping from names to IP addresses associated with specific, domain name suffixes. And so the top-level domain name servers for .com is there, .org, .edu, .mobi, you name it, there's one for it, right? And a lot of practices for different countries, like .fr for France, and so forth. And so when a client issues a query, that query is directed to the root DNS server. So if I type www.google.com, first it goes to the root, and then the root says, hey, that's a .com. You really need to contact the top-level domain name server for the .coms. And then the .com says, oh, that's for Google. You really need to contact Google's domain name server, and this is its address. And so essentially what this hierarchy implements is this forwarding of whom to contact, and then ultimately you're forwarded to the DNS server for that particular organization, which has the IP address of that server in particular that you're looking for. Okay. Any questions about this? Does that make sense? So we'll pick back up on Tuesday with the balance of DNS and hopefully get through the rest of the application layer. Again, we have a homework due on the 11th, which is Tuesday. I look forward to your solution.